So I'm trying to tell you a little bit about our incremental reasoning agent. At first, I'll give you a problem statement. So what is the thing we're actually trying to solve with the agent? Then I'm getting into expert systems a little bit and explain what is a knowledge base and what's an inference engine and what are all those words about. Then I'll give a brief introduction to CLIPS so that you can actually read it and hopefully also write it. Then an introduction to our world model, how we are modeling our world model in CLIPS, and well, a bit in-depth information so you can use it. And afterwards, a little bit about reaction and interaction with the world model. So how can you use it and how can you react to certain states in the world? After that, I'll give you a short summary and a lookout, well, what can you do with this? And afterwards, I'll give you a short introduction to the hands-on you should be doing afterwards. So first, what's our problem? So the problem that we are trying to solve overall is a strategic mission. So this is what our agent is trying to solve. And what's our mission? Well, of course, it's achieving the maximum score we can in the game. So this is what we are trying to achieve. And the mission can only be achieved if we're doing the right decisions at the right time in the game. So if we react correctly to the current world state, well, at least we'll try to get the maximum of points with this. And what are the actual problems in the logistics league? So we have a high complexity and dynamic of the production chains. So because we have all those different products and we don't know what we have to produce beforehand, this is a very complex and dynamic problem for us. The individual robot, which is running the agent for us, does have incomplete knowledge about the world. So the robot only always knows about the stuff it can see, or it gets communicated from the other agents, but you never know the whole image of the world. And what's very important is that the plan breaks due to non-deterministic events. So the simplest thing is that a machine might be down. So I don't know how many of you know it, but sometimes the ref book says, okay, machine cap station 1, for example, will be down for 30 seconds and it'll show a red light, but you never know beforehand when this will happen. So you can't plan this into your planning. And well, also your robot might break or something. And what you have a lot, especially at the RoboCup, are communication breakdowns. So there's a lot of Wi-Fi noise, and you almost never have a really constant Wi-Fi connection. So that's why we are also doing a lot of stuff locally. And yeah, last but not least, of course, we have robot breakdowns. So yeah, you might have noticed Focus is also not running totally stable. So sometimes you're doing a quick fix like 5 minutes before the game, and yeah, you have to take out the robot again and fix it. So we have to deal with at least a part of the robots going out of the game for some time. So why did we choose an expert system to tackle this problem? So at first, in an expert system, we have the representation of the world state through a knowledge base. So in this knowledge base, we're collecting all the information we have about the world. And why did we do this with an expert system? So at first, it has a very good readability. You can actually read the current world state in the web interface, and well, of course, you have to know a bit about the facts, etc. But if you know what's meaning what, you can easily read it and you can just see it. There's nothing coded or something like with hashes or IDs or whatever, but you can see what the state is all about or what maybe the robot is thinking the state is. And on top you have situation-specific rules. So you're formulating rules to a specific world state and then you're reacting on these rules. And you can also read these rules very easily. And you can see, okay, if I'm in this state, I'll be doing that. And rules are non-scoped. So if you're thinking about a normal decision process in computer programming, most of the time you will have if-else constructs. And then often you will have an if construct in another if, and then you have a scoping problem because you won't see stuff that's outside of the if construct. And we don't have this problem with rules because they are non-scoped. The expert system is very transparent, so you can see this in the logs later. If you're looking at the log, you always see why special case is executed, or well, why this skill was called. So you'll explicitly get a rule that is executed, and then you can go into the rule and see, okay, that's why it happened, and that's what I have to fix. And a very important point is adaptability. So it's very easy with an expert system to start with a simple world model that has only a few features, and then you can extend it step by step, but it keeps running and you don't have to rewrite everything. I hope you'll notice this later in the hands-on. So where's the agent in our behavior architecture? So it sits on top of the behavior engine you just used in the hands-on. The reaction with the world is basically only skill calls in the behavior engine. So yeah, we're steering the behavior from the agent, and we're basically, you can see this, planning what actions will be executed. Now I want to talk about the knowledge base and the inference engine of the expert system. So at the core we have the knowledge base. What's in this knowledge base? We have runtime information. So this is information like, okay, I did this and that, and then I know, okay, I will be in this state, or, well, I picked up a base, probably I have a base in my gripper, hopefully. We have external information, for example, from the ref box or from other agents, so from the other bots, and we have sensory information from the sensors and actuators. So this is our current world state that is in the knowledge base. And what are we doing with this knowledge base? We're actually using the inference engine, which has a fixed rule set. So this is what we as experts are defining. And we say, okay, in this specific world state, we'll execute rule A, and then the action will be executed. And how do we get all the data in there? So what's the external data we're putting into the knowledge base? So as I already said, it's primarily at first the sensors. Like the laser, and I think what we're actually using is the tag vision, so we can see if there's a tag scene, etc. The actuators, like the gripper, so to check, well, do we have something in the gripper, and yeah, can we do something with this? And most important are the skill results. So did the skill we just executed, did it succeed, or did it maybe fail? And then we can check in the world model that's in the knowledge base, well, why might it have failed? So, well, maybe we don't have a base anymore in the gripper and our driving skill failed. So maybe, well, we just hit another robot and lost the base. So we can correct that. So again, the scope of the knowledge base. So what's really all in there? At first we have the cooperative agent information. So this is information we are getting from the other agents. This is, for example, machine location and type. If you're thinking about the exploration phase, when the robots are driving around and trying to find the machines, you possibly only find 1/3 of the machines, well, roundabout, and you'll get the other locations and types of machines from the other robots. The same goes for locked positions. So we're, for example, locking something like the in and output sides of the machines and products. So, well, we won't drive with 2 robots to 1 machine. And we're seeing this is locked and we can't go there. We have game information from the ref box. We are constantly getting the orders. So what's currently ordered, the current machine state. When a machine goes into production, for example, the ref box will notify us. So that's also put in there. And also very important is the game time. If you think about the game being paused, the game time will stop and your internal time will be useless for you. So, well, you also have to get the current game time from the ref box. And at least the sensory information, so for example, as I already stated, the tag detection or our gripper state. How is knowledge actually represented in our knowledge base? I have 2 examples here. One type is the machine, a machine, so this is a template for the machines, and this is a template for an order. So what's actually in there? For the machine, we have stuff like the machine type at first, so that's most important because we want to do what we can what we actually can do at the moment. We have the logs, so do we have any products or robots incoming to the machine, or can we use it? Do we have bases in the machine in production, or maybe do we have bases put into the slides, etc. So this is saved there. The position we need for the exploration phase, and the current state the machine is in, and of course the production time. I'm actually not that sure if we're using this right now, but this is an estimate for ourselves how long the production might take, so we can estimate when it will be finished. The same goes for the order. We at first have a product ID, so which product is ordered with this order. So you'll have a matching product fact to this order where the product itself is defined. We have the complexity of the product, the delivery gate in which you should put the product in the delivery station, how many quantities of this product is ordered in this order. Well, it can be more than one, so that's important. How many we have in production or in delivery, and well, again, the time. So this is a delivery time window. We have a start and an end time in seconds given from the ref box when we have to deliver this product. So that's important. You have to keep in mind when producing. This is always about delivery and not about production itself. So we are using Clips to write our agent. So a short introduction. So Clips is a rule-based production system, and it's a first-order logic forward chaining system. I don't know how many of you are acquainted with the logic, but maybe you heard the word before. The production is actually executed with condition action rules. So you always have a rule that has a certain condition, and then an action will be executed. You have two types of memory. You have a working memory that holds facts. So these facts, or this working memory is actually the knowledge base from before. This is our short-term memory, so the memory we have per game. And we have a long-term memory. This is our heuristic knowledge that is encoded in the rules. So this is actually the knowledge the expert puts into the system and encodes the system to tell the system what should be done at what moment. So about Clips itself, the full name is C Language Integrated Production System. It uses a graph-based RCLL algorithm. It has Lisp-style syntax. So I don't know if you're used to Lisp, so it has a lot of parentheses. So you will have to get used to that. It features typically large rule bodies and a relatively small number of facts. So in our current agent that we use at the RoboCup, we had 224 rules and only 49 different facts that we had defined, so 49 different types of facts. But what you can see is that you have a lot of changes. So we had over 200,000 changes in 10 minutes when we are playing a game. So there's a lot of stuff happening in the knowledge base. And what's a plus for us, since Fox is using C++, it integrates very nicely also with C++. So for the terminology, I want to introduce four important keywords for you. The first one is facts. So the fact, as I already said, is basically what is encoded in the knowledge base. This is a complete fact. Well, it's missing some attributes, but you can always see the name of the fact at front. So this is machine fact. And then you have the attributes. So the attributes are in green. So we have a name and a machine type. And for example, in this example, the machine name is M-CS1, and it's a cap station, obviously. What's special about facts is that you can have incomplete knowledge, and you're also encoding knowledge when you're not having it. So you might state it explicitly, so you can set the type to unknown. Well, if you're still exploring the machine, then you have the type unknown. So you know, okay, I still have to explore this machine. Or you also can have non-existent facts. So for example, you might have the whole machine missing if you didn't explore it yet. So you can get out of this that you don't have the machine yet. The next keyword are functions. So this is our procedural knowledge. These are simply, that's more or less very similar to every other programming language you might know. So we define a function. This is the function name, and you get the input variables. And in this case, this function simply computes the string of the navgraph point for an output of a machine. So we're simply extending the string with a -o to say, okay, this is the output. The third are the rules. So this is what you will be basically working with, or what you will be writing. This is our heuristic knowledge, the knowledge you will put into the system. I will come back to the rules later, but you can see, okay, you have a def rule and a name, and you have here a condition. And this is, after the arrow, this is what is getting executed. So this is the action you're actually taking. And at least you have the agenda. So on the agenda are the currently active rules. So what's happening is that, well, when something gets added to the knowledge base or to the fact base, all conditions of the rules will be checked. And for all the rules whose conditions are met, they will be put onto the agenda. And then Eclipse, well, looks, okay, which rule does have a higher salience and puts this on top. Or if they have the same salience, well, this is not totally defined which will be what will be executed, so you better have some salience in place to manage this. And the rule that is on top of the agenda will be executed, and the other rules, well, they won't be executed, but only on the next fact change they will be checked again, and then they will, well, maybe be executed or not. But you have to think about this, that you only have one rule active at a time. So what does our current world model in Eclipse look like? First, we have two different kinds of facts. We have ordered facts and structured facts. So you see, ordered facts are pretty basic. You only have the fact name and the value, or, well, maybe multiple values, but you don't have multiple attributes, but only this one. And in structured facts, you have the fact name and different attributes, and then you have values for those. You can add ordered facts as you like. You can name them as you like. Eclipse won't say anything, but you still have to map them later. So I have some examples. So this is the game time we're getting from the ref box. Our team color. So this is cyan at the moment. The holding fact states if we're holding something in our gripper. So at the moment that's none. The game phase we're in, so this is a production game phase. These are the same names as are used in the ref box. So if you want to check it, it's always the same. And this is our robot state. So it's idle and it's not doing anything at the moment. And this is an example for a structured fact. So this is a ring. Because the required bases for the rings are randomized for each game, we have to keep the rings also in our fact base. And we know in this fact, okay, it's a blue ring and we need one base for the blue ring. Now we're going on to the machines. So this is a simple machine. So for us, simple machines are the base and delivery stations because they don't have any totally special function, or we don't save anything in there. We have, as you saw before, the name and the machine type. We have the team, of course, so we also have information about the machines of the other team, so especially something like the position, etc. If we have some product incoming or another robot incoming, so if something's locked at this machine, if we have a product loaded, or if we have a product produced at the output, so there will be an ID in here then, and the current machine state. So this machine isn't doing anything at the moment and is ready for production. What we are doing with the other machines, with the ring and the cap station, we have an extra fact for them. It's very convenient to have this additional fact, because you don't have to clutter the normal machine fact with the additional keywords. We're also having facts where we're doing this actually, which is not looking so nice. So maybe you'll see this. Then you see why we're not doing this here at least. And yeah, you can see, for example, so there's a product produced at the output of the machine. So this is the ID. We'll come to the products later. And this is actually a cap station. And these two facts are mapped to each other via the names. So this name is identical, so you know it's the same machine. And this is the state of the machine, so it doesn't have a cap loaded in the slide at the moment. And what we are currently doing, because it's simpler for us, is we assign a cap color to the cap station. You can have gray or black caps, but it's easier to replenish and to plan for us at the moment because the agent isn't, well, that complex at the moment. So we have a fixed color for the cap station. So this is the cap station we are using for the black caps. Then we have the order. You might remember it from earlier. So we have an order ID. This is the ID we are getting from the ref box. This is the product ID, which product has to be produced in this order. And again, complexity and the delivery gate, etc. So you see the begin and end times here. So that's important. You can see this is an order for the whole game. So it's from 0 to 900 seconds. And we have here if we are currently producing something, if we are currently producing a product for this order or not. Now we're coming to the product, so this is the most confusing part. We will fix this, but we didn't fix this yet, so you have to deal with this. I'm sorry. So this is the product order fact. So this is the template, which kind of product you will have to assemble. So you see, this is the same idea we had in the order, and it's a product with a black cap and a red base. So the basic product you also, well, some of you produced in the other hall, I hope, with the skills. And this fact is the real product. So this represents the products we are driving around the playing field. This maps to this product with this ID. So we say, okay, the product we are assembling, or we hope to assemble, is this one. So we want, at the end, to have a red base and a black cap. And in this real version, we currently only have the red base. So probably we just got the product out of the base station and have to move it now to the cap station, put the cap on, and then deliver it. So these facts, these attributes of the fact will get updated in every step in the production. Yeah, so these were the basic facts you will need for your tasks later. Now, how do we react and interact with our world in Clips? So first, we are formulating rules. Why would we want to do this? First, we simply want to process information we get put into our knowledge base or communicated by the other agents. We want to trigger skills to drive somewhere, to produce something, etc. And what's very important is to check for world model sanity. I already mentioned this, so sometimes your world model breaks and you definitely want to correct it, otherwise you're doing stuff you can't do anymore and you won't make any points. So what does a rule basically look like? You always start with the def rule keyword, followed by a rule name. You can optionally make a comment. We're actually doing this now for all our production rules, but I think the rest isn't that much documented. In the declaration, you can, for example, declare the salience. You probably won't need this for this hands-on today, but in the reproduction, you want to have this if you want to produce a lot of different stuff. And then the most important parts are you have a left-hand and a right-hand side. So this refers to this arrow. On the left-hand side of the arrow, you have the conditions for the rule you want to have met, and on the right side, you'll have the actions you want to execute if the conditions are met. So, starting with the most important things first, how do we bind variables? There are three things you want to do with variables you can do in Clips. So you can match facts against each other. So if you want to match the facts, you actually always read the first time you have a variable, so they always start with a question mark. These are variables. You bind the value of the team color, which was cyan, I think, into this variable. And if the variable occurs again, it will be matched. So well, you can think of it as a query or something. So you'll only match machine facts with the team cyan here. So that's important. You're only getting the binding once and then you're matching it. Another use is binding the address of a fact. So if we want to remember an address of a fact to, well, maybe modify it later or delete it, etc., you can read it with this arrow to the left and then you're writing it into the variable. So we are writing the ID of machine into the variable m. And of course, maybe you want to reuse the value of of a variable to, for example, well, execute a skill and give the skill something or compute something, etc. And then you can simply also bind the, well, in this example, we're binding the ID of the loaded product of the machine. So next, how do we get new stuff in there and why would we do this? So typical stuff is adding a new task to a production step, or maybe correcting a broken world model, or well, writing the logs from we're getting from other agents into our world model. You can simply add facts with the keyword assert. So assertion is always adding something to the knowledge base. And then you simply state the fact as you would read it also in the knowledge base. So this is very straightforward. Next, we can also remove old facts. So why would we want to do this? So one very important step is just to remove clutter from the knowledge base, so you can still read and use it. Of course, facts may represent an old world state you want to get rid of, or rules might fire continuously due to unchanged conditions. So you're having this a lot, that you're not really changing the world model with your rule, and then something might change in the fact base and the rule will get executed again and again. So you have to remember, okay, I have to change the conditions, otherwise, well, there's at least a chance that it will fire all the time. So if you want to remove a fact, you simply state the retract keyword and a variable with a reference to the fact. So you saw it earlier when we were at the machine fact. So in this example, it would be retract $m, then you could delete the fact. So what we can also do, and is well, it can be read a lot better, is modifying facts. Because most new knowledge that we are getting into the knowledge base is only partial knowledge. So for example, a state change in the machine, so you only want to change the state and not delete the whole fact and assert a new one. You can actually selectively modify facts, so only one attribute can be modified of a fact. That definitely increases readability and maintainability because, well, you don't have that much code and it's easier to read. But what it's actually simply doing, it of course executes a retract and assert, but you don't have to hassle with this and don't have to get all the variables to rewrite the stuff. There's one catch: you cannot modify ordered facts. So this is only for facts for structured facts. So the ones with the attributes you define in the def facts section. You can modify a fact with a modify keyword. Then you state the reference to the fact and then the attributes you want to change. So in this case, you're changing the state attribute to running, but you might also state more attributes you want to change, as many as you would like to. And at last, we come to conditional changes. You can do conditional changes on the right-hand side if you simply want to, well, do another change for one simple conditional element. So for example, I think in the example, there's only one, well, Boolean that we check, and then we want to assert something else in the, on the right-hand side. So you do not want to have two facts that look basically the same and have only one different keyword. So you can handle this like that. This is a lot more readable, and it's definitely easier to find errors if you're using something like this. So if you want to have an additional condition, you simply can say it if, so like you use from normal programming languages, and then the condition, and then you can also do anything you like as you would normally do on the right-hand side with the actions. So after this, a complete rule. So this is a pretty basic rule, but a complete one. So you can see again with def rule, a name for the rule. We don't have any comment in this one, but we are declaring a salience here. So we are doing this in a kind of configuration file. So this is a global variable, and we have all these conditions. So our robot has to be in the production phase, idle, and so we are reading here the team color from our knowledge base to map it to the machine we want to select. We make sure that we are not holding no product, so this is not none, and this is a normal AND relation. So we save the ID of the product we are holding, and we don't want it to be none. Then we are matching here the product with the product ID, so we get the product, and then we are actually trying what the fact says. We are discarding an unneeded base. So we are here asserting the state and the steps we have to do for the task to be fulfilled. So this is actually, if we have an unneeded base and we want to get rid of it, we normally just put it into the slide of a ring station that doesn't have 3 bases loaded already. Yeah, so as a quick summary, utilize the agent to make strategic decisions in the game. So this is what the agent should do. You shouldn't do all the micromanagement. So this is what the skills should do. So the behavior stays in the skills, but you are doing the strategy in the agent. You represent your knowledge in the knowledge base or in the fact base, what is called in clips. You can see it in the web interface. I have a link later. You're doing decisions on the basis of the current world state. So we are not doing something like planning ahead or something, but it's always responding to the current world state. And we use the skiller you just had in the other hands-on to interact with the world. What our agent is it's a local distributed incremental agent. So what we want to say with this is local, so it makes all decisions on the single robot. It doesn't communicate for the decisions with the other robots or something, so it's only on the local world state. It's distributed, so every robot is doing it himself, and it's not, we don't have a centralized planner or something. And the agent is incremental, meaning it only plans its next step one at a time. So we are not doing the complete planning. And well, what we think is that the agent level is the biggest opportunity for diversification in the logistics league, because, well, you can do a lot different there and have very, very different strategies, and so this might be the thing you will maybe want to do you want to do otherwise. So like having a global planner on top of an agent, or only having a global planner and hope that everything goes well, or, well, whatever you like. So this is what you should take with today. And I'm now doing a bit of hands-on. So I only give you the first task for now. I hope you can do the other task tomorrow. So at first you simply should try to recognize the start of the production phase. So when you enter in the production in the ref box, well, your robot should be doing something. The first task is simply use your waypoints you have on your current navigational graph and, well, try to drive around the machine with the agent. So call ppgoto or so as a skill, and then simply, well, make waypoints and make sure that you notice, okay, I arrived at point 1 and then I want to start the next step, etc. So this should be your first steps to get acquainted to clips and the, well, not so syntax. And afterwards you should be able to react to game phase changes. So maybe you also want to stop when the game is pausing, etc. You should be able to call skills from the agent, handle finished skills. So you will have a state of the skill in your knowledge base. And well, yeah, you should also be able to model a production process through consecutive skill calls. So you should call them one after another, and yeah. Let's see how far you come today, but yeah, I think it's doable. So for the informations, I will provide a download. I will put it on the wiki when we're going down. You can extract it in the agent folder. So in this folder, you'll find the agent files. If you want to check on the current world model, you can do this in this address. So this is where you see a fact base and what your current world state is. The Clips programming guide, which you will definitely need, can be found here. And you start the simulation with this command. So what's new for you most probably is the -A option, which starts the agent that is configured. Okay. So, any questions?